computational knot theory. Thank you for inviting me as a speaker. The purpose of this presentation is to give the precise value of the total number of all knot mosaics. To do that, we construct an algorithm producing the exact value. This is a joint work with Hwa Jeong Lee, and Hwa Lee. Before we get started in earnest, let's define knot and link. A knot is defined by a simple closed curve in three-dimensional Euclidean space R3. Here we have two examples, a knot, a trivial knot, and triploid knot. And link is a disjoint union of knots in R3, which may be tangled up together like this. Okay. In this talk, we use the term knot to mean either a knot or a link. Here, these figures are projections onto a plane, your slide, with the height information at each double point. So we call the double point crossing and the projection knot diagram. Okay. So actually, a knot mosaic is a spatial knot diagram. So first, I will introduce knot mosaic, and then we construct an algorithm to count the number of knot mosaics. Okay, what is a knot mosaic? In 2008, Lomonaco and Kaufman introduced knot mosaic system in the paper Quantum Knots and the Mosaics. The theoretical background, why they consider the system, dates back to modern physics. The quantum mechanics is a theory that explains the movement of infinitesimal particles such as atoms and electrons. Okay. Then Lomonaco and Kaufman thought knot theory will be a tool for exploring quantum mechanics. Then their objectives are to create a quantum system that simulates a closed knotted physical piece of rope, and to define a quantum knot to represent the state of the knotted rope, and to model the ways of moving the rope around. In 2008, they introduced a knot mosaic system to define a quantum knot system. Okay? As I mentioned before, today, we only consider knot mosaic. Okay? So please refer to the paper for details of quantum knot system. Okay. Let's move on to the main subject. What is a knot mosaic? A knot n mosaic is a representation of a knot on an n by n grid composed of 11 tiles as depicted here. So up to rotation, there are 1, 2, 3, 4, 5 tiles. Okay. Here we have two examples of 4 mosaics. Triploid knot 4 mosaics, a non-trivial, non-knot 4 mosaic. Okay. Now, let's take a look at the 11 tiles. In each tile, the endpoint of a curve in blue is called connection point. Okay, here. Okay. 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 I'm sorry. Just put right. Okay. Yes. So in each tile, the endpoint of a curve is called connection point. Okay. Then you can check each tile has either 0, 2, or 4 connection points. Okay. Right. Next, a tile in a mosaic, for example, the tile in yellow in A, okay, is said to be suitably connected if each of its connection points touches a connection point of a contiguous tile. Okay. So in A, all tiles are suitably connected. Okay? But in B, there are some non-suitably connected tiles in green. So a non-mosaic that can be defined as a mosaic with all tiles suitably connected. Okay. So furthermore, we can figure out that the tiles on the border, called the boundary tiles, okay, cannot have 4 connection points to be a knot. Okay. In their paper, Lomonaco and Kaufman proposed interesting questions related to knot mosaics. Now, some of them are as follows. Okay. Now here, the first and second questions are pretty natural. Okay. Is there a relation between mosaic number and crossing number? And determine mosaic number of knots. Here, the mosaic number of knot K is the smallest number n among all knot and mosaics of K. So in 2014, so we found a relation, and in 2018, so we determined the mosaic number of all prime knots with up to 8 crossings. Okay. Next. They asked how many knot and mosaics are there. Okay. So this study is inspired by this question. Okay. Okay, let's turn to the second part of this talk. First of all, how many 1 knot mosaic, 2 non-mosaics, and 3 knot 3 mosaics are there? Okay. There are only 1 not 1 mosaic, and 2 not 2 mosaics. Okay. And in the appendix of Lomonaco Kaufman's paper, they gave a complete table of all not 3 mosaics. There are 22 in total. Okay. And in our study, we generalize their question in random rectangular form. So first, we define knot and n mosaic. A knot and n mosaic is a representation of a knot on n by n grid composed of the 11 tiles. And you let n be an n by n matrix of mosaic tiles. And bold n to the power of mn be the set of all mn mosaics. Okay. The knn be the set of the subset of n, the subset of the set mnn of all knot mn mosaics. Okay. Here n means mosaics, k means knot. Okay. And dnn be the total number of elements of knn. Okay. Since there are 11 tiles, this number is obvious upper bound of dnn. Okay. Here, as listed before, this page shows all elements of K11, K22, and K33. So D11, the number is 1, the total number is 2, and the total number of the D33 is equal to 22. Okay, next. Now, what is here is the main theorem of our study. For integers mn greater than 1, the total number dmn of all lot mn mosaics is 2 times. It's given by 2 times the double absolute value of this matrix. Here, the double absolute value means the sum of all entries of the matrix n. And xn minus 2 and on minus 2 are given by partitioned matrices or block matrices inductively defined as follows. To prove that, first I introduce one observation called twofold rule. This observation says that if the inner tiles of a mosaic board are suitably connected, suitably placed, the inner tiles means tiles that are not boundary tiles. Okay? Here, all tiles within the pink boundary are inner tiles. Right? So if the inner tiles of a mosaic board are suitably placed, then there are only two ways to complete the board so that it is suitably connected, resulting in a knot. For example, look at the place in green. Okay. For this board to become a non-mosaic, the tile must be one of two tiles. Right? And then, so we can naturally complete a knot for each case. So therefore, in order to prove our main theorem, we first count the total number of suitably connected inner boards, okay, of knot MN mosaic, and then we apply this twofold rule. Right? So here, the double absolute value means the total number of suitably connected inner boards of size n-2 by n-2. Okay. And then we apply twofold rule. Okay. Then we have the number. Okay. Okay. Now let SPQ be the set of all suitably connected PQ mosaics, SPQ, that possibly have connection points on their boundary edges. Okay. As mentioned just before, each element of SPQ, okay, can be extended to exactly two knots by the twofold rule. So for example, you can see that, okay, given a suitably connected 5-3 mosaic, okay, then we can have 2, 7, 5, not 2, not 7, 5 mosaics. Okay. Next, let SL be the L state of the suitably connected mosaic, which indicates the presence of connection points on the boundary, left boundary edges. If the L means left. Okay. Here, so from now on, so we use the symbols O or X depending on whether or not the edge has a connection point. Okay. So, and the order of the state will be given from top to bottom, right? So, in this case, the L state of S53 is OXXOX. Okay. In the same way, we define the right state of the suitably connected mosaic and denote it by SR, right? So in this case, SR, the R state of S53 is OXOXO. Okay. Now we have two remarks. The set SPQ has 2 to the power of P kinds of L states and also the same kinds of R states. Okay. Because the number of row is P, right? Then we arrange the element of the set of all states in the backward of lexicographical order, such as XXX, OXX, XOX, OOX, XXO, OXO, XOO and OOO, or P is equal to 3. Okay? Substituting X and O into binary 0 and 1 respectively, it will be easy to enumerate. And now, to count the number of the set, this set, okay, we construct a matrix called the state matrix. Right? So a state matrix for the set SPQ is a this size square matrix NPQ. So here, each entry Nij is the number of all suitably connected PQ mosaics that have the I's L state and the J's R state, I's L state and the J's R state in the set of all states. Okay, here we have an example. N22 is the state matrix for S22. There is 2 by 2 suitably connected non-mosaics, suitably connected mosaics. Okay. Now, since a suitably connected 2 by 2 mosaic has 2 rows, the mosaic has 4 L state and 4 R state. Right? And the order state is XX, OX, XO, OO. XX, OX, XO, OO. Okay. So here 16 in yellow means that there are 16 suitably connected 2 by 2 mosaics with XX L state and XX R state. Here XX L state, XX R state. Right. Then the sum of all entries of N22 is 1297. Okay. Therefore, we have the total number of all not 4 mosaics, T44. It is 2594. Okay. So T44 is given by 2 times this value, okay, by the two-fold rule. Okay. Then starting with N11, let's construct the state matrix. Right? Now, the first we consider bottom state X and O. Right? Then 1 by 1 mosaic can have 2 L state and 2 R state like this. Okay, first we consider bottom state, and then we consider left state and right state. Then each tile is automatically determined like this, right? Because the number of connection points of each tile is 0, 2, or 4. Okay. Then depending on the bottom state, we split the matrix N11 into 2 matrices, X1 and O1. X is from the bottom state X, O is from the bottom state O. The hills, each 1-1 mosaic represent each entry 1 of X1. Okay. So for example, this entry is from this tile, the number of this tile. Right? The L state is O and X, R state is X, O, X, and the bottom state is X. Okay. And this 4 is from these tiles, right? Then L state is O and R state is O. So all tiles have the same state, right? Therefore, so we have N11. Okay, the N11 is given by X1 plus O1. Okay, then we have the number 11. So actually, we know that the number of tiles is 11, right? Here, so by the two-fold rule, each element of S11 can be extended to exactly 2 not 3 mosaics, not 3 mosaics, right? This implies the 3, 3 is equal to 22. Okay. Okay. The proposition 1 shows that the state matrix NP1 or SP1. Okay. So for the set SP1 of all suitably connected P1 mosaics, then the state matrix NP1 can be obtained as follows. Okay. Here XP and OP OPs are defined by like this. Okay. Okay. Now we'll prove the proposition. We'll prove the proposition 1. Okay. The first, the identity follows from the definition of XP and OP. Okay. And to prove this part, okay, we use the induction on P. Okay. The two matrices X1 and O1 are already found in the previous page. Okay. So we assume that matrices XK and OK satisfy the statement. Okay. So given a suitably connected K by 1 mosaic, okay, then now we add one tile and consider the bottom state and the bottom state. Okay. Then the yellow tile can have two L state and two R state, like this. Okay. Then the top state of each tile in yellow is automatically determined like this because of the number of connection points. Okay. Then the number of K plus 1 by 1 number of all suitably connected K plus 1 by 1 mosaics with this condition is equal to OK. Okay. And in this case, the number of all suitably connected K plus 1 by 1 mosaics with these conditions is equal to 4 times OK. So we can establish two matrices XK plus 1 and OK plus 1. So because of the backwardness of lexicographical order of 2 to the power of K plus 1 states. Okay. Here, the number of all suitably connected K plus 1 by 1 mosaics with these conditions represent here. In this case here. So do we complete the proof? Okay. So now I introduce proposition 2. Proposition 2 is about NPQ for SPQ. For the set SPQ of all suitably connected PQ mosaics, then the state matrix NPQ is the following. Yes, first, so here, so first we assume that NPK, okay, first we assume that this identity holds for Q is equal to K. Okay. Then let SPK plus 1 be a suitably connected PK plus 1 mosaics in this set. So, okay, for example, we have a suitably connected P by K plus 1 mosaics here. Okay. Here, let's take the last column of the mosaic and say SP1. And let the remaining part here be as pk, like this. Okay. Oh, I'm sorry. Okay. Then, so we denote npk plus 1, the state matrix for as pk plus 1, where each entry nij count the number of all suitably connected pk plus 1 mosaics that have the i's L state and the j's R state in the set of these states. Okay. Similarly, we can denote npk and np1. Okay. So here, it looks very complicated, but the main idea is from here. Then, okay. This entry is the number of cases in which R state as pk and the L state of sp1 exactly match. For example, here, like this. Okay. So this means that npk plus 1 matrix is expressed as the product of two matrices and okay here. So this means that npk plus 1 is expressed as the product of two matrices npk and p1. So this implies that the identity. Okay. So we complete the proof. So finally, I'll give you main theorem again. So okay, in our main theorem, the two means a twofold rule, and the value means the number of all suitably connected n-2 by n-2 mosaics. Okay. So from the idea of the twofold rule and proposition 1 and 2, so we can prove the theorem. So finally, so we summarize our findings in this table. Okay. So indeed, this number grows the exponential rate. And in 2019, Kim and O proves that this rate, that they called this number not mosaic constant or entropy. Okay, that's all. Any questions or comments? Okay, thank you very much.
Thank you.
Yes, okay, I have one question. So the question is, okay, here. So how did you compute those numbers shown in the last slide? Okay, this table, right? Then the number is from our main theorem. Then we compute this using MATLAB. Yes, thank you.
Do you have any guess about the significance of that limit of Kim and O? It's bigger than 4, but what should it be?
I don't know exactly, but they get this value only.
I must apologize for joining late. I had a problem with my connection.
No problem.
That's okay. That's okay. So are there any other questions? Okay, Hwa Jeong, thank you very much. Okay, thank you. So that's all for this session. We will continue tomorrow morning for those who like to join at 10 a.m. with Professor Toshitake Kono, who is going to speak about some unitary representations of break groups. Okay. Okay. Thank you very much.